Hello, these are the solutions to recitation activity 8. This activity is taking place over fall break, so those with Thursday recitations will not be meeting in person, but instead you can watch this video to go over the solutions. And then those with Tuesday recitations, it's actually not a required attendance day, so you can skip without any penalty or without using one of your 2 allowed drops. Anyway, so a photon with a wavelength of 2575 is most nanometers is most likely in what region? Well, here's what I would remember. I would remember that the visible, and this is the only range I would want you to really know for sure, is that it's about 400 to 750 nanometers. And then we would go higher wavelength would be the IR, then microwave, and then radio frequency being actually really long wavelength, about a meter in distance for radio frequency. And then shorter wavelength would be UV, and then X-ray and gamma ray. And so really high energy, low wavelength here, in the middle, visible. So we're just a little higher than the visible, so probably in the IR region. You may have been a little confused if microwave was a choice and which choice is better, infrared or microwave, but I think infrared or microwave are the best choices. Radio frequency would be much, much longer, and then these are definitely not the right answer. Question 2, copper metal must absorb radiation with a minimum frequency of 1.15 hertz, 1.15 times 10 to the 15 hertz in order for an electron to be ejected. What wavelengths of light can cause an electron to be ejected from copper? So the idea here is the energy is equal to h nu. As long as the energy is higher than this threshold, so long as we go to a higher frequency, then electrons can be ejected. If you go to hc divided by lambda, then we want to go to a lower wavelength. So lower wavelengths are greater energies. So we want to go to some lower wavelength, not some greater wavelength. So the answer should be B or D. And then we're just calculating the wavelength from the speed of light, c is equal to lambda nu. And so the wavelength associated with this electrons being ejected from copper would be lambda is equal to c divided by nu. So 2.998 times 10 to the 8 meters per second divided by 1.15 times 10 to the 15 inverse seconds is a hertz. And that equals 2.61 times 10 to the minus 7 meters. 1 meter, 10 to the 9 nanometers would be 261 nanometers. If we go lower than 261 nanometers, then electrons can be ejected. Which transition leads to the 411 nanometer transition in the hydrogen emission spectrum? So we have to have emission, so we have to go from some high end state to some low end state. So we have to go from a high to a low energy state in order to have emission, otherwise it would have been absorption. And so this rolls out B and C. So only A and D go from a high to a low end state. But notice that if you think of n equals 2, verse 3, verse 4, verse 5, verse 6, let me draw this one more time, trying to get this to scale, because we have n equals 3 here, then 4, then 5. So as we go up in energy, our states are getting closer together. And so 6 to 2 transition is going to be a greater energy than a 3 to 2 transition. And so the 3 to 2 transition, this is lower energy. If you happen to remember, the hydrogen emission lines went from about 410 to 656 nanometers. The 656 nanometers are lower energy transition. Our higher energy transition is going to be the 6 to 2. And so this is probably going to be the 6 to 2 transition. We can verify this one of two ways. We can just um, plug the numbers in and see, or we can try to solve out since the final state is 2 for both of these. What we might do is write that our change in energy is our E final minus our E initial. Our energy is a function of N. For hydrogen is minus 2.179 times 10 to the minus 18 joules times 1 over that N value squared. And then another thing we might write is that this change in energy here is what this 410 or 411 nanometer line corresponds to. And so the photon energy is telling us the change in energy for the atom. The energy of our photon is hc divided by lambda. And so if I just do that math, That's going to be 6.626 times 10 to the minus 34 times 2.998 times 10 to the 8 divided by 411 e to the minus 9. So that's 4.833 times 10 to the minus 19 joules. And that's the change of energy for the atoms. The atom's losing this energy, and then the photon's gaining the energy. So our delta E here, the atom loses energy, so our photon energy is positive. The delta E for the H atom here, for the electron in the H atom, has to be negative 4.833 times 10 to the minus 19 joules. The atom's losing energy, so I have minus 4.833 times 10 to the minus 19 joules here. And it's going to be equal to the final state, where n is 2, and our initial state, which is, either 3 or 2, or 3 or 6. So we can just plug in and solve, or we can try to solve for that n value. And so I'm going to have minus 2.179 for the final, times 10 to the minus 18 joules, times 1 over 2 squared, and then minus negative 2.179 times 10 to the minus 18 joules, times 1 over that n initial squared. I'll do some math here. So I have negative So I have negative 4.833 times 10 to the minus 19 joules. I'm going to add to that 2.179 second e to the minus 18, divide by 4. That gives me 6.14 times 10 to the minus 20, 6.142 times 10 to the minus 20 is equal to negative 2.1, actually it's plus, so it's negative times negative, so plus 2.179 times 10 to the minus 18 joules times 1 over that n initial value squared. And so what I want to do here now is just divide both sides by 2.179 times 10 to the minus 18. So my 1 over n initial squared is equal to 0.02819. And so I just need to do some cross multiplication. So put n I squared over here, then divide both sides by 0.02819. Maybe I've rounded something a little bit wrong. This is about 35 and a half is equal to the ni squared. So ni squared is equal to about 35.5. Take the square root of both sides. Literally going blind. Oh, there it is. Yep, so it's 5.95. This is 6. So ni is equal to 6. So the initial value is 6, going down to 2. So again, this is a relatively, for the visible spectrum, this is the highest energy peak. The other peaks are lower. So the lower energy peaks would be 5 to 2, 4 to 2, 3 to 2, and then this peak here would be from the 6 to 2 transition. We could also use we could also just have said, well, what wavelength would this correspond to? Which wavelength would this correspond to? We'll see that this is about 656 nanometers, and this is that 411 nanometer line. What is the de Broglie wavelength of an electron with the velocity of this? So this wavelength here is equal to h over mv. So this is the wavelength of matter. I can call this the de Broglie wavelength. Is just from taking Planck's constant, 6.626 times 10 to the minus 34 joules times seconds. Now my mass here, I need to put this in kilograms. So an electron mass is equal to 9.109 times 10 to the minus 31 kilograms. I'm expecting that you would look this up on my chart, like in the daily quizzes. There's a sample info chart that's listed there. That's why you don't see it in the problem. This would probably just be told you in the problem. If for some reason you have to calculate this on the test, they always give this to you in grams and try to trick you. So you just have to divide by the mass in kilograms, 9.109 times 10 to the minus 31 kilograms. And the reason why is that the joule is a kilogram meter squared per second squared. So in order to cancel out into the units of joules, you got to put mass in kilograms. Think SI units, that's why we don't leave it in kilograms. And then the velocity is 6 times 10 to the 6, 6.00 times 10 to the 6. The plus and minus has nothing to do with this problem. That's for the uncertainty principle. And so meters per second. And so we cancel everything out here except one of the meters. So everything cancels out except for meters here. So 6.626 times 10 to the minus 34. Divide by 9.109 second e to the minus 31. Times 10 to the minus 31 divided by 6 times 10 to the 6 gives me 1.21 times 10 to the minus 10 meters. 1 times 10 to the minus 10. Let's 1 meter is 10 to the 10 angstrom. So 1 meter, 10 to the 10 angstrom. So times 10 to the 10 gives us a value of 1.21 angstrom. So the uncertainty, or excuse me, the wavelength of the electron is on the scale of the size of the atom. So we have the wavelength on the scale of the actual orbit size of electrons spinning around an atom. So it's important to describe and understand that electrons have a wave-like behavior. What's the minimum uncertainty? The uncertainty principle says that the minimum uncertainty in the position times m delta v has to be greater than or equal to h over 4 pi, just a fundamental limitation on how we can know the simultaneous location and velocity of a particle. And it really only becomes the really light particles where this becomes a practical limitation on where a particle is. Think of a baseball, we know where it is and what its velocity it is at any given moment. We can see it when it's thrown. It's not like we all of a sudden have a larger size in the baseball probability distribution that we're seeing. But for an electron, that's what we'd be seeing. We'd be seeing more of a distribution where we expect to find the electron as opposed to a discrete particle. And so now the way this problem would work here, the minimum possible uncertainty in the position, that's delta x. And then the electron with this velocity, it's the uncertainty. It's how certain we are in the velocity. So it's the 0.050 times 10 to the 6 value that comes into play with the uncertainty principle. So we would take our delta x greater than or equal to h divided by 4 pi m delta v, which would be greater than or equal to 6.626 times 10 to the minus 34 kilograms meters squared per second squared times seconds, so joules times seconds, divided by 4 pi 9.109 times 10 to the minus 31 kilograms again, because we're talking about electron as the particle, and then the velocity, the uncertainty of the velocity is 0.06, or excuse me, 0.050 times 10 to the 6. So we use the uncertainty, the plus minus value. This is our delta V. And so I think this comes up to 12 angstrom. So 6.626 second e to the minus 34 divide by 4 times pi times 9.109 e to the minus 31 times 0.05 e to the 6. So I get the number in meters, and I multiply by 10 to the 10 angstrom per meter, and that gives me 12 angstrom. I get 2 sig figs here, around 2 sig figs, so I get 12 angstrom out. So that's a pretty big uncertainty, right? Like that's a really small, excuse me, a really big uncertainty for a relatively ordinary electron that we might be picturing in an atom. So this just leads to the idea of electrons behave as waves, but as waves is more of a distribution or a probability distribution than a discrete particle. Why did this? Well, this problem we already did, so we don't need to do it again. Which set of the following quantum numbers are allowed for an electron in an atom? And so it just goes n starts with 1 up to, essentially infinity. But practically speaking, for atoms, it's going to stop well below infinity. But the range of L is 0, all integers between up to n minus 1. M sub L goes minus L through 0 all the way to plus L, all the integers between. And M sub S is the only fractional one, plus a half or minus 1/2. This is where we get 2 electrons per orbital. And so looking at the first three, we have a 3D subshell, excuse me, a 3P subshell for the first one, but this M sub L is impossible. M sub L has to be for this L, minus 1, 0, or plus 1. It can't be minus 2. So 1 is impossible, and then 2 is impossible well, because if n is 2, the max L can be is 1. It can be 0 or 1, but not 2. So neither 1 or 2 are allowed. What's the designation for the n equals 4, L equals 2 subshell? Well, L equals 0 is S, L equals 1 is P, L equals 2 is D, L equals 3 is F. I don't think we'd ever ask this on the test, but 4 just goes H, 5, I, or F. My goodness, I don't know my alphabet. It would be F and then G, and then H, etc. If you go to even higher values of L. So 1P, 2D, 3, F. So this is the 4D subshell. Now you don't confuse yourself. You could have the 4S, the 4P, the 4D, and the 4F subshell with this S value. It's just that your L is going to be 0, 1, 2, or 3. What is the maximum number of electrons that can occupy the 5F subshell? The 5F subshell is n equals 5, L is 3, that's what F is. And then the M sub L range is minus 3, minus 1, minus 3, minus 2, minus 1, 0, 1, 2, 3. So that's 7. So I get 7 orbitals that can have that occupy the 5F subshell, 2 electrons each, so that's 14. What is the range of possible values for the magnetic quantum number M sub L for this orbital? The key here is that this is showing a d orbital. If it's a d orbital, L is 2. And if it's L is 2, the range of M sub L is minus 1, minus 2, minus 1, 0, 1, 2. And so is it 2? Must it be 2? No, it could be 2, but it doesn't have to be 2. It's one of these values here. It's minus 1, it's minus 2, minus 1, 0, 1, or 2. Just one of those numbers. So it could be this range here. So C is the best answer. And its L value can't be 0, 1, or 2. The L value is specifically 2. So this question said, well, what is the range of angular momentum quantum numbers L? The only value there possible is 2. So the only n possible, well, the n range, so if he said the same question, what is the possible n value for this orbital? You could say, well, n could be 3, because that's the first time we have a d subshell, or 4, or 5, etc. How many unpaired electrons does a ground state sulfur atom have? So sulfur has 16 electrons. It has it's in the third row of the periodic table. For the full configuration, it's a 1s2, 2s2, 2p6, 3s2, 3p4. It lands underneath oxygen. Oxygen's a 2s2 2p4, so we have a 3s2 3p4. If we count up our electrons, so this is 10, that's the neon configuration, and then plus 2 plus 4, so 10 plus 6 is 16, so that checks out. And then the unpaired electrons we get from our valence diagram, going 2, 3s2 electrons, but there's 3p orbitals, so 1, 2, 3, and then 4. So we get 2 unpaired electrons. Which atom contains 4 valence electrons? So 4 valence electrons will be the carbon group, so tin and lead will follow suit. So all of these have 4 valence electrons. So if you know iodine, you say, how many valence electrons does iodine have? Well, I come to fluorine. Fluorine is a 1s2, 2s2, 2p5, has 7. The whole way down the chart should have 7. Now you could also work out for something like, iodine. We did tin and lead in our lecture notes, but iodine would be a krypton configuration straight before xenon. It would be a krypton, and then followed by a 5s2, 4d10, and a 5p5. And so notice we're not counting these 10, no, they don't disappear, but they don't count towards the valence. But the outermost shell, these count, so we have 7 valence electrons. The highest shell. Highest shell is n equals 5. So these would have 7 valence electrons, just like fluorine has 7. 13, vanadium, commonly found with these charges here. How many valence electrons does ground state vanadium have? Well, vanadium is in the first transition metal series. I think it's the third transition metal. Yes, it is. And so vanadium has a total of 23 electrons that we have to distribute. Let's start with argon for 18, 4s2, 3d3. And so sometimes we land on a half-filled D subshell is more stable than like a not half-filled D subshell. But this is the true and actual configuration. So it's a predicted and actual configuration of vanadium. Don't get too confused on predicting anomalous configurations. Just be able to give our predicted configurations. And this is the actual one too. But anyways, we would have 5 valence electrons for this atom, 3 unpaired electrons. So 5 valence, wasn't asking for the unpaired, but we'd have 4s2 and then 3d, 2, 3. 14, an atom with this anomalous configuration, what is the element? How many total unpaired electrons does the atom have? So krypton, 5s1, krypton's 36 electrons, plus 1 plus 5 would give me a total of 42 electrons. So I'm looking for element number 42, and that should be molybdenum, and it is. So this is molybdenum. And then we have a total of 6 unpaired electrons. I have my 5s1, my 4d, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So 6 valence electrons. What is the electron configuration of neodymium, which does not have, we're told it doesn't have one of these anomalous configurations. If we ever just ask you for configuration, we always need the anomalous configuration. Sometimes in mastering chemistry, they might expect that you double check that chart in the textbook. But neodymium, ND, there is an ND element 41, but that's not what this question is asking about. ND is in the lanthanide series, it's element number 60. NB is niobium, element 41. So this is element number 60. And so we would be following suit here with element 60 coming after xenon. Xenon 54 electrons. And so xenon would follow into the 6th row, so 6s2, and then 4f for the remaining 4. So we'd have a 4f4. So 54 plus 6 gives us 60. So that's the right count. So we'd be a 4f4. So we got to make sure we do these choices carefully, but it looks like xenon 6s2, 4f4. All right, that's all. Thanks for your attention.